The last simple machine we're going to look at is the lever. Um, Lever, there are very simple applications for this, so we'll look at a couple of examples of everyday levers that you may encounter, but it's also the one that's a little bit more complicated because there's different cases that you can have with them. So let's just look at them. So first, a lever is just an object with an arm that pivots on a fulcrum. There are three classes of levers. The first, and I have the pictures here, so this is the first class lever. Fulcrum is just something it balances on, or your pivot. So in this case, it's the red triangle. So a first class lever will have a fulcrum between the input force and the output force. Output force, once again, is the weight of the object, and input force is what you are exerting on it. So whenever the fulcrum is in the center of the two forces, that's a first class lever. Your IMA is always going to be greater than 0. So that's not really telling you much at all. It's just a number, any number greater than 0. An example of a first class lever would be pliers. A second class lever, you're going to have the output force right here in between the fulcrum and the input force. And there your IMA is always going to be greater than 1. The example that I'm going to give you for that would be a wheelbarrow. So think this is where the wheel is, this is the load of the wheelbarrow, and then this is where you are lifting it up. And then the final one we're going to look at is a third class lever. That's where the input force is between the fulcrum and the output force. An example of a third class lever would be the human arm, where the fulcrum is your elbow. The input force is coming from the muscles that are connecting your lower arm to your upper arm. And the output force would be any object that you're holding in your hand. So that would be a third class lever. Now off to the side in your notes, I realize there's not room there, but if we go to draw, just want to show you a basic thing with a lever and make a little distinction here. So here's a lever, here's a fulcrum, here's the object, and let's say I have an applied force over here. So this would be my input force, here would be my output force, and input distance and output distance are not the distance to the fulcrum. So let's say you push on the lever over here and you cause it to move down. That would be your input force. Pushing down on the lever would cause this to move up. That would be your output distance. So when you're looking at the distance between input force, output force, and the fulcrum, that would be something different. And we're going to call that, so from here to here, that would be the output radius, and from here to here would be the input radius. I'm going to pull trig again. So because these would make triangles, and they would be similar triangles, so you have an angle here, and let's see, this would be R out, so the angle here. The ratio, so IMA, we know, is D in over D out, but we're not always going to be given D in and D out. The ratio will work exactly the same to say that for levers, IMA can equal R in over R out. So yes, IMA is D in over D out, but for levers, and let me make this distinction, for a lever, it would be R in over R out, where it is the input radius, distance between the input force and the fulcrum, and the output radius, distance between the object and the fulcrum. You could be given either, but like I said, a lot of times you'll be given these radii. Because of similar triangles, we can use this. One more word of caution. Whenever you're solving for work, work equals force times distance. So you cannot use R in and R out as distance. Distance would have to still be D in and D out. We'll just do one example. So looking at this lever, it tells you the box has a mass of 52 kilograms and requires 62 newtons of force applied to the right end of the lever to lift the object. So your applied force is going to be right here. That would be my F in. Because the fulcrum is between, so fulcrum is between the object and the input force, this is a first class lever. We're looking for the IMA and the percent efficiency. It gives us 30 meters, which would be R out, and 24 meters, which would be R in. F in was 62 newtons. And then it tells us the mass of the box is 5 kilograms. Fg equals mg, which equals F out. So 5 kilograms times 9.8 newtons per kilogram equals my output force. This would be 49 newtons. So IMA for levers is R in over R out, which equals 24 meters divided by 30 meters. 24 divided by 30 equals 0.8. We are looking for a percent efficiency. In order to get that, we also need the AMA. So AMA equals F out over F in, which would equal the weight of the mass, 49 newtons, over the input force, 62 newtons, and that gives us 0.79. So for percent efficiency, AMA over IMA equals 0.79 divided by 0.8, and we get 98.8% efficient. So with levers, it depends again where the fulcrum is, where the object and where the input force are for what your IMA should be. The IMA, you can use the radii, but don't get confused. Radius is not the actual distance over which the force is exerted.